Welcome back. In this short video, we're going to talk about the so-called handshaking lemma. I'm not kidding, it's called handshaking lemma. It's very useful in many arguments in graph theory. So please do pay attention. So you have a graph G, and which is denoted by a pair V and E. As we talked about before, V is the set of vertices and E is the edges connecting vertices, including loops if you have any. It's a finite graph. Again, what it means is the number of edges and the number of vertices are finite, as you'll see in these examples. The statement of the handshaking lemma says if you add the degrees of each vertex, if you take the sum of the degrees of all vertices in a graph, that equals twice the number of edges. Okay? That's it. That's the theorem. So if you compute the degree of each vertex and add them up, that sum, this is the sum, equals 2 times, this is your cardinality of E, that means the number of edges. That absolute value of E is the cardinality of E. Let me get a better marker. Cardinality of E, also known as size of E. Size of E. In other words, the number of edges. It's a very important lemma. I'm going to prove it in the next video. The proof is not that complicated. But let's try to verify this lemma in these two examples. The handshaking lemma. So what we need to do is we got to compute the degrees of all these vertices. You have 4 vertices here in this first example, Königsberg bridge problem, and let's compute D of A. D of A is how many are attached to A? 1, 2, 3. Degree of A is 3. Degree of B is 1, 2, 3, 4, 5. All the edges that are connected to B. Degree of C is all the edges connected to C. There are 3 of them. So degree of C is 3. Degree of D is 1, 2, 3. And you have seen this before. We computed these degrees in the previous video. Now, the handshaking lemma says if you add them up, so sum of the degrees, sum of the degrees of all vertices, so we have 4 of them, you got to add all those things. That is 3 plus 3, 6, 6 plus 5, 11. There are 3 9s here, so 9 plus 5, 14, sorry. So 3 plus 5, 8, plus 6 is 14. Okay? And that's the left hand side. That's the sum of all the degrees. The right hand side is, they're saying that number should be twice the number of edges. Let's count it. You could see from the picture there are 7 edges here. There are 7 edges. So this is 2 times the size of the set E. E is consisting of E1, E2, E3, E4, E5, E6, and E7. So it's twice of E. So it's checked here. Okay. Let's try to do the same thing here. So in this case, you got to compute. As you can see, the edges are, the edge set is consisting of F1, F2, F3, F4, F5, F6, F7. So F1, F2, F3, F4, F5, F6, F7. There are 7 edges in this graph as well. And let's start to compute the degree of each vertex. D of U1. D of U1 is 1. There's only one edge here. D of U2, let's go in an order. D of U2 is 1, 2, 3, 4, 5. There are 5 edges connected to U2. Degree of U3, 1, 2, and 3. There are 3 edges connected to U3. Degree of U4, U4 is F5, F7, F6. Pause for a second. If you have a loop, we are counting that as 2. Remember, every loop contributes 2 to the degree of that vertex. So degree of U4 is 1, 2, and 2 for this loop, F6, so it's 4. Okay. And degree of U5. Degree of U5 is just 1. So if you compute the sum of all these degrees, it's 1 plus 5, 6, 9, 9 plus 4, 13, plus 1, 14. So here, the sum of the degrees is, this number for this example is 14. If we add the sum of all those degrees, that's left-hand side. What's the size of E? Size of E is again 7, because there are 7 vertices. Therefore, 2 times 7 is 14, so this is checked. So this handshaking lemma is, like I said, is a very useful tool in solving some problems. So once again, what's the handshaking lemma? If you take a graph, whether it has loops or no loops, if you add the degrees of all vertices, that's what this left-hand side is, that should be equal to 2 times the number of edges. Okay? Thank you.